Section 2.4, we are going to learn how to find derivatives of products and quotients. That's what we're going to focus on today, where you can't maybe just multiply them out or divide them out. In the last section, we saw that sometimes we can handle certain products, certain quotients, because we can simplify them algebraically, but that will not always be the case. So we need to know, what do we do with these other products and quotients? And so first we're going to start with our product rule. And I'm not going to take the time to go through the proof, but you can see your definition of the derivative here, and then really a lot of algebra that gets done on this. So we start with our definition of the derivative, limit as h goes to 0 of the original function with the x plus h, so f of x plus h, g of x plus h in this case, minus the original product function, f of x, g of x, all divided by h. Then we go through and we add in this fancy zero is what I call it. So we add in, there's only a couple of things that we can consistently always do algebraically, and it's multiplying by versions of 1 and adding in versions of 0. So here we add in a version of 0, and then we break this into two different terms, kind of reorder some things a little bit here, and then factor out some GCFs. And so what we end up seeing in these two situations is we're going to end up, if you kind of follow through the algebra, take your limit and observe what you end up with, you do end up with the product rule at the bottom there. So our product rule says that in order to take a product, essentially you leave one of the factors of those functions as it is, and then you multiply by the derivative of the other factor, and then plus you change that order, and then so like in this case g left alone, and then times f prime. So f times g prime plus g times f prime is how we can describe what to do in order to take the product of two functions of x. So let's jump in here and take a look at some examples. So we have something in this first example, x cubed minus 2x plus 1, that quantity times the quantity 3x squared, x to the fourth, minus x squared plus 2e to the x. So we have something that in theory, you could, if you wanted to, you could certainly multiply all that out if you were so inclined, but that would take a little while to multiply out two trinomials. And there are certainly going to be situations, we'll see one in the very next example, where you don't even have that option. So we're definitely going to work with our product rule on this one. So what I want you to observe is we do have a function of x times another function of x. So this tells us then by our product rule that our derivative, so we'll denote that dy dx, is going to equal, and here's how your derivative works, it's going to be the f left alone, and then times the derivative of g, and then plus, you're going to change that order, and it'll be g left alone times the derivative of f. All right, let's jump in and fill in these functions. So f left alone, all right, x to the third minus 2x plus 1 times the derivative of g. Okay, these are just nice power rules from the last section. So 12x cubed minus 2x, and then plus 2e to the x, derivative of e to the x is e to the x, plus, and then changing that, and now isolating g, or I should say isolating, just taking g left alone. So 3x to the fourth minus x squared plus 2e to the x, and now times the derivative of f. So that's going to be 3x squared minus 2. And that's it. We're not going to spend a lot of time on some of these here, going through and multiplying everything out. If I was going to do that, I would have done that in the very beginning to take the derivative, right? So we're looking at ways to take the derivative that don't involve multiplying everything out, so why multiply that all out in the end? In fact, when we get into moving through here, kind of complicated types of like products and quotients, a lot of times how we simplify them will more involve kind of looking at both of these terms and seeing if there's a GCF that we can factor out. So that's more the type of simplifying that we'll be looking at, is really going to involve factoring out a GCF if possible. But in this case, it's just kind of getting used to your derivative. So that's our product rule. Okay, let's look at another one. So number 2, the binomial of x to the third minus 1 times another binomial, x e to the x plus 2. So again, I do have a product of two functions of x. I have an f of x here times my g of x, the f of x being the x to the third minus 1, and the g of x being the x e to the x plus 2. So let's start by again taking our derivative here. And as we look at our derivative, we're going to start with that outer structure of saying, okay, this is going to require product rule. And so, or I'd have to multiply it all out, but even then, something's going to happen here a little different. So let's just kind of set up what this would look like, of course. So we would have f left alone, and then we're going to have times the derivative of g, and then plus, we'll change that up, and then we're going to have g left alone times the derivative of f. So that's the outer structure of my product rule. All right, so let's jump right in here. F left alone, x to the third, oops, that was minus 1, times derivative of g. Now, the derivative of g, that first term that we're looking at there, the x e to the x, that is its own little product of two functions of x. So you have to treat x, oh, and I didn't mean to erase that whole thing here. I just wanted to give myself a little more room. Bear with me, my apologies here. So let me just rewrite this. So this was my x e to the x. So we had identified that as being this outer, this whole binomial. This was our g of x. But now, within that is its own little product. X is a function of x, and so is e to the x. This is a product of two functions of x. It's not just 2 e to the x or 7 e to the x, it's x e to the x. So this is going to require its own little product rule. So let's say that this is, let's call these functions, how about h and maybe j or something. So I have an h of x times of j of x, but I have a product of two functions of x. So that is going to require me to do a little product rule in here. So let me just give myself a little bit of room here. All right, so within this structure, actually I'll write it below. So I'm going to have an h of x times, that was a j, wasn't it? So h left alone times the derivative of j, and then plus j left alone times the derivative of h. All right, so h of x left alone, that's just my x, times derivative of e to the x, so j prime is e to the x, plus changing that order. Now the second factor left alone, so e to the x, the j of x function if you will, and then times derivative of h, well that is of course just 1, derivative of x is 1. And then kind of returning back to this binomial, of course the derivative of a constant goes to 0. I'll just kind of put that in for that outer structure here. So here what we have is a product rule taking place within a product rule. And an important, that inner product rule is noting how for the first time now we see not all functions can just be, we can't just circumvent the product rule. I can't just say, well, I'm not going to learn this new product rule thing that she's talking about. I'm just going to multiply everything out. I like to multiply things out. Okay, not going to be the case, especially soon we're going to get into trig functions and all sorts of stuff. All right, now I'm halfway through my product rule. Let's get back to it. So now it's g of x left alone. This is another good reason to sometimes have that structure laid out sometimes you get deep into like an iteration of a problem and you forget you still had like another term to fill in here. And then times the derivative here of f prime, well, that's just 3x squared. So there's my structure. And then, I'd probably just kind of leave it like this. I'll rewrite it just because I had like that plus 0 in there, and that looks kind of weird. So what do I have? I have x to the third minus 1 times x e to the x plus e to the x. And then plus, probably put the monomial first, 3x squared times x e to the x plus 2. So there's my derivative, dy dx, or y prime if you prefer. Now let's find the equation of the tangent line to this function at x equals 0. So this is our part B. So remember, if you're going to find the equation of the tangent line, that means you need the good old slope of your tangent line, specifically evaluated at x equals 0. And then you could jump right in and just sub in 0. And so that's what we're going to go ahead and do. So we're going to say, all right, well, that would look like 0 cubed minus 1. 0 cubed minus 1 is just minus 1. And then times, well, the first term, again, x is 0. And then plus e to the 0, well, e to the 0 would just be 1. And then now plus in my second term, 3 times 0 squared is just going to be 0. And then really 0 times anything, it happens to be that would be 2, is still, of course, just going to be 0. And so the slope of my tangent line here is -1. So there's my slope. And of course, if we need to find the equation of a line, there's two things we need. We need the slope, and we need an xy ordered pair. So if we have, a lot of times your homework may give you both the x and the y coordinate. I just like to a lot of times make us go over that because students often will make the mistake of subbing into the derivative as opposed to going back to the original. So 0 cubed minus 1 is just going to be -1 times, going back to the original, x e to the x, well, that's going to be 0 in the first term plus 2. So this is going to be 0 plus 2 is going to be 2. And so that was subbing back into the original, and we get -2. So now we have our xy ordered pair, and that's everything we need to find the slope. And the point is everything we need to find the equation of the tangent line. Also, in this case, if we notice, our life just got a lot easier if we note in this example, because we're at the point 0, a number, 0, -2 in this case, that is actually the y-intercept. So think about plotting that on your coordinate plane. So the y-intercept is -2. And that, of course, is your b coordinates when you're going into y equals mx plus b. So actually, I don't really have anything to even do here. I can go right to the final form of my equation of the line. And so we get to go right to our y equals mx plus b. Our m in this case is our -1. And our b here is the -2. So we end up, of course, we probably just say -x minus 2, y equals. So there's the equation of our tangent line at x equals 0. All right, so there's a couple of examples with the product rule. Let's now introduce the quotient rule. So the quotient rule we're going to write out here. The proof would follow in a pretty similar way as the one that I laid out for the product. So we're going to start off, except this one's going to have, it's a fraction, and in the denominator, you're going to start off, and it's going to be the denominator function, g of x quantity squared. That g of x is what you're going to start your numerator with, and then you're going to say that times f prime, derivative of the numerator, minus, and then changing that order, it'll be the numerator function left alone times the derivative of the denominator function. So that is your quotient rule, similar to the product rule, but here's what we have to note. The order now matters. So it's important because of subtraction, the order now matters. Addition was commutative. So not only, of course, is there this fraction, and you have this g squared in the denominator, but it's subtraction and the order will now matter because of that subtraction. So there's lots of catchy ways to memorize this. I like to just kind of think about whatever function I'm starting with in my denominator and I square it. That's the original denominator. That's what I start with left alone in my numerator. However you want to learn this, you will have to, have that kind of committed to memory. Definitely. All right. So let's take a look at this first example. So we have f of w. I think I'm guilty of doing too many functions of x all the time. So we'll call this one f of w equals 3w squared minus 5 over 4w squared plus 7w. So we definitely have a quotient of two functions of w in this case. There's no way to avoid quotient rule here. You don't just have a monomial in the denominator where you could maybe simplify, divide and simplify it. So we're going to jump right in here. We're going to apply our quotient rule. So our f prime of w is going to equal, okay, so again, we're going to have a big old fraction bar here. And we are going to start with, we're going to have that original denominator is going to be squared, and that is what goes in my new denominator. Now that's what I'm saying. I use that as my prompt to say, oh yeah, the order matters, and I'm going to start with 4w squared plus 7w. I'm going to start with my denominator left alone in my numerator. That's what I was saying. That's kind of how I memorized it. Once I know that, the rest would fall into place. So if it was denominator left alone, then it would have to be times the derivative of the numerator, so 6w. It is subtraction, and now I change that up, right? So if it was the denominator left alone in the first term, my second term now needs to be the numerator left alone times the derivative of the denominator, so 8w plus 7. Okay, and that's basically it. Again, right now I'm not focusing on much in terms of simplifying. I mean, you could distribute through the 6w, I suppose, if you wanted to, or multiply out those two binomials. I will say this, a caution, that as we do get into some simplifying, right now we're kind of focusing on just learning these derivative rules, but something that students often do that's an important caution is that they often are tempted to reduce, or their favorite phrase, your favorite phrase is sometimes cancel. You cannot do any reducing here because of the subtraction that you have in the numerator. If you had all multiplication in the numerator, you could, but you can't here. You have subtraction, okay? So don't do that. All right. Number 2 is where our book kind of rolls out the power rule. They prove it really here is what we're going to do. And we're going to now prove the power rule for negative exponents. So what I want us to think about here is we're taking the derivative with respect to x of x raised to a negative, and then the p represents a positive number itself. So this is a positive integer. So this is like x to the negative 4th or x to the negative 2nd or something like that. So that, if we remember our just basic algebra of working with negative exponents, is equivalent to 1 over x to the positive p. And so now remember, this is my little differential operator. It says take the derivative, and then the denominator says with respect to x of this 1 over x to the p. So now when I take the derivative, I now know how to do that with quotient rule. So quotient rule says, again, how I kind of like to think of it here is I'm going to start with my denominator, x to the p, and of course that gets squared in my denominator. Then that's my prompt to kind of start with my x to the p left alone, denominator left alone, up in the numerator. And here, we want to be a little careful, the x, here that, I'm going to just fix this, hold on just a second here, that looked really sloppy, so this is x squared. Okay, the derivative of the numerator in this case, derivative of 1 is 0. So this whole first term is going to be gone. However, the subtraction is still there from the quotient rule. Now we change the order of what we were doing, and now it's the numerator left alone, 1, and then times the derivative of the denominator, which we have proven the power rule for positive exponents is p x to the p minus 1. All right, so what do I now have here? I have negative p x to the p minus 1 power, all divided by x to the powers we multiply, so 2p. Then this negative p is just really like a constant multiple. Dividing with the same base, rules of exponents tell us that we subtract the numerator exponent, subtract from that the denominator exponent. So this is going to give me negative p x to the p minus 1 minus 2p. So p minus 2p is negative p minus 1. And that is the power rule of x to the negative p. So x now raised to negative exponents, that's my power rule. So we've now shown with the quotient rule, we've shown that the power rule holds for negative exponents, negative integers, I should say, negative integers. It'll actually hold for all real numbers, but we're kind of rolling this out in stages in terms of our proving of this. So let's use that then to take a look at this next example. So g of x equals 4x to the negative third. Oh, I can now use my power rule. Plus 2 over x plus e to the x over x to the third. So let's take a look at this. G prime is going to equal, so power rule. Bring down the negative 3, that's going to be negative 12. And then just be careful, you're subtracting 1. So negative 3 minus 1 is going to give you negative 4. Now you have two choices with this 2 over x. You can leave it like it is and do quotient rule, or you can realize, well, wait a second, I can rewrite that and just think of that as really being, instead of using quotient rule, I now know that's the same thing algebraically. We already knew. Algebraically, that's equivalent to 2x to the negative first. And now we know we can do power rule. So we could just say, oh, that's going to be negative 2, bring down the negative 1, multiply by the 2, and then x to the negative 1 minus 1 would be negative 2. So that's kind of handy. I like to do that in particular when the numerator is just a plain old number, because then I get to avoid doing quotient rule, and when I bring it up, it's not a product rule, it's just a constant multiple. However, in a situation like this last term, if I bring up, and it's okay to do it, but if I bring up x to the third as an x to the negative third, this is still going to require me to do product rule. And you're welcome to do that. My personal feeling is if all I'm doing is replacing a product rule, a quotient rule problem with a product rule problem, I haven't really saved myself anything. So I tend to bring it up as a negative exponent in something like the second term when there's just a constant in the numerator, because then I get to avoid both quotient rule and product rule get avoided. But in this last term, I mean, I don't know, product rule, quotient rule, they're about the same amount of work. So I would probably gravitate towards, in the last term, just leaving that one like it is and doing a quotient rule. So that's what I'm going to do here. But just be mindful, if you chose to bring it up, that's perfectly fine. But you would have needed product rule at that point. All right, so we're going to leave it like it is and just do a little quotient rule. So again, quotient rule starts with that denominator being left alone. It's in my new denominator, but this time it's squared. That's my prompt. Start with just denominator left alone in my numerator. And then that's going to be times numerator left alone. Quotient rule is subtraction. Then change the order. And so now it's going to be the e to the x left alone. So e to the x's are always weird, right? So we just had the denominator, in the first term it was denominator left alone times derivative of e to the x, which was e to the x. Now it's minus e to the x left alone times the derivative of the denominator, which is 3x squared. So that's what we have there. Let's clean this up just a little bit on kind of any of these if we wanted to. So maybe in the first term, a lot of times with negative exponents, you can leave them like that, I suppose. But you do want to get really efficient at just making sure your algebra skills are strong in terms of being able to go back and forth in between, negative exponents and positive exponents, and we'll get into some radicals as well. So you want to make sure you're really efficient at that. In this last term, what we might do is do a little factoring out of a GCF in that numerator. So I could factor out an e to the x, and I can also factor out an x squared. When I do that, in the first term I would just have x, and then minus, in my second term I'm just going to have 3. And that whole thing though is still over x to the 6th. And by factoring out the GCF, it does allow me to do a little bit of reducing here. I can reduce the x squared factor with the x to the 6th, and that leaves me with an x to the 4th in the denominator. And then if you really wanted to get kind of in a nice form final answer here, notice the first and last term already have an x to the 4th denominator. You could multiply your second term by x squared over itself, and now you have a common denominator all the way across. So your final answer could look something like negative 12 from the first numerator minus 2x squared from the second numerator, and then from the last numerator we have e to the x times the quantity x minus 3. And this is all over x to the 4th. And you could maybe reorder some things if you wanted to. You could distribute through the e to the x again and, clean things up. But I'll just go ahead and leave it like that. I mean, you could maybe rewrite a few things there, but nothing more would factor out and reduce or anything. So again, technically, all of these are just equivalent forms of the derivative, but that one's a little bit more cleaned up there. All right, so I'm going to stop there for this video. When we come back next time, we are going to take a look at a graphical example, and then we're going to move into higher order derivatives next time.